Okay, guys, today we're going to start our Unit 6B, which is all about gases. Make sure that you are utilizing the pause button so that you can pause the video and write down the notes. And make sure that you pause it before the second example so that you can try these problems on your own before I explain them again. So when we talk about gases, we talk about them being ideal gases. An ideal gas has no volume, which means the molecule itself is not taking up space compared to the space between the molecules. Now, in a real gas, we know that they really do have a volume, that particle itself is taking up space. Ideal gases do not have intermolecular forces, so they're not attracted to each other and they're not repelled by each other. But we know that in reality, there are intermolecular forces. So a real gas has intermolecular forces. An ideal gas follows the gas laws that we're going to talk about. And a real gas differs somewhat because of the volume that it's taking up and those intermolecular forces. So you just have to understand that when we go through this unit, that we're talking about ideal gases and not real gases. And so with some of the things that we're talking about, if you were to go and measure them out in the real world, it might not measure exactly the way we're saying it. Now, there are three things that we measure. We measure pressure, temperature, and volume when we talk about gases. So first off, there's pressure. Now, pressure can be measured in several different units. It's all measured with a barometer, though. A barometer is what the picture is in the bottom corner. So you have a pool of mercury, and it's kind of like an upside down graduated cylinder. And the atmospheric pressure pushes down on the surface of the liquid, and it goes up into the tube. And so that the height of the mercury inside our upside down graduated cylinder tells us what the atmospheric pressure is. If you listen to the weather, you might hear it referred to as the barometric pressure. There are 4 different units of pressure that you have to be aware of. The first one is ATM. ATM stands for atmospheric or atmospheres. If we were to take our barometer down to sea level, the measurement of the mercury would be 760. So that's the second unit, 760 millimeters of mercury. Now we call that 1 ATM. So instead of having to deal with very large numbers, we can convert that to ATM and it'd be a nice, neat unit. Torr is named after the chemist Torricelli, who did a lot of experiments with pressure. So he's honored by giving him the unit torr. Now, torr and millimeters of mercury are the exact same thing. So in that case, we can just erase the letters and change the unit, but the numbers would remain the same. Our last unit is kilopascals. So there's the K, kilo, as in King Henry. And then we have pascals. Now, Pascal was a chemist who did a lot of experimenting with gases and pressure. And so again, we honor him by giving him a unit of pressure, the kilopascal. Now, 1 ATM is equal to 101.3 kilopascals. So it's not as big as millimeters of mercury. However, kilopascal is a very large unit if you think about it in terms of pascals. It would be times 1,000. These numbers are given to you in your reference table on page 1. So if you look at page 1 of the reference tables, the bottom of the first box, or towards the bottom of the first box, you have the units of pressure given to you, and you have these numbers given to you. So it's your responsibility to know how to convert from one unit to the next. So we're going to look at 2 examples. So in the first example, we have 1.75 ATM, and we're trying to convert it to kilopascals. So we're going to go from ATM to kilopascals. This is just like converting grams to moles. It's one step, nice and easy. So we're going to start, of course, with our given, because we always start with our given. Our given unit is ATM, so we're going to bring that down to the bottom so that we can throw it away. And then we're trying to get to kilopascals, so kilopascals would go on the top because that's the unit we want. Then we look at the number line on our reference table, and we see that 1 goes with ATM, and 101.3 goes with kilopascals. So all we have to do then to find our answer is multiply and divide. So 1.75 times 101.3 divided by 1, and we get 177. Now I only used 3 significant figures because our given 1.75 is 3 significant figures. When we multiply and divide, the ATM will cancel, leaving us with kilopascals as our answer. All right, so we're going to try the second example. We're going to start with our given. Here we have torr, and we're trying to get to ATM. So we're going to take torr, and we're going to move it down to the bottom so that we can throw it away. And then our unit that we're wanting to get is ATM, so we're going to put ATM on the top. We look at our number line on the reference table, and we see that 760 goes to torr, and 1 goes with ATM. So now we're ready to solve, and we're going to do multiply and divide. So 570 times 1 divided by 760. Again, I use 3 significant figures. This first 0 does not count because it's in front of the decimal, in front of the number. This 0 at the end does count because it's after the number and there's a decimal. We're using 3 significant figures because in our given, we have 3 significant figures. That decimal is making the 0 significant. When we multiply and divide, torr divided by torr is going to cancel, leaving us with ATM. Temperature. There are 3 different units of temperature. Hopefully you've watched that video. We are not going to talk about Fahrenheit at all because that's only used here in the US. We're going to focus on Celsius and Kelvin. Now, when we're working our math problems, we have to be in Kelvin because Kelvin does not have negative numbers. The formula for converting Celsius to Kelvin is Kelvin equals 273 plus your degrees Celsius. This is given to you on page 3 of your reference table. So if you ever forget 273, you can look at page 3 in your reference table and see how to convert. You are always going to convert your Celsius to Kelvin. So here's our first of 2 problems. Convert 65 degrees Celsius to Kelvin. So all we have to do is take that value and plug it into our equation. We're looking for Kelvin. There's the constant 273, and we're just going to add 65 degrees Celsius. Now, when you add and subtract, the significant figures are based on decimal places. And since 65 does not have a decimal place, then my answer just needs to be written as a whole number. So we get 338 Kelvin. Kelvin also does not have that degree symbol as Celsius and Fahrenheit does. So it's just the big letter K. The second example, we're given 262 Kelvin and we're trying to convert it to Celsius. So this time we're going to plug the number in to where the Kelvin is in the formula, and we're going to solve for Celsius. So in order to get X by itself, we're going to have to subtract both sides by 273, and we get negative 11 Celsius. Remember, Celsius can be negative, but Kelvin is not, and that's why we use Kelvin in all of our math problems with gases. Now, the last thing that we have to measure is volume. This is something that we've actually done before, way back in Unit 2. We talked about how 1 mole is equal to 22.4 liters. What I didn't tell you back then is that it has to be at STP. So anytime you see at STP in a problem, you just have to recognize that this is simply converting and there's no special formulas to use. Now, STP stands for standard temperature and pressure. On page 1 of your reference tables, that top box is showing you what standard temperature and standard pressure are. So those things are given to you again. So when we go to convert, we always start with our given. And in this case, it's 7.08 moles of nitrogen gas. Remember, nitrogen is a diatomic. It is part of Hofbrinkel, so it's going to be N2. Now we're starting at moles, so we're going to bring mole down to the bottom so that we can throw it away. And we're looking for liters. Volume. Volume is measured in liters, so we're going to put liters on the top. And then we can look at page 1 of our reference table, and we can see that 1 goes with mole and 22.4 goes with liters. So now we're ready to solve the problem. We're going to multiply and divide. When we do that, mole cancels mole. We get 159. I use 3 significant figures because our given has 3 significant figures. Because mole cancels, we're left with liters of nitrogen. Let's try one more. Now this problem is a little different from our last problem because this one gives us a reaction. And when you're given a reaction, that means this is a stoichiometry problem. So this is bringing back Unit 5 that I know you guys enjoyed. So the first thing that we want to do is we want to balance the reaction. We have 2 nitrogens and 1 nitrogen, so we're going to put a 2 here. That gives us 6 hydrogens, so we need to put a 3 here, and our reaction is balanced. Now we always start with the given. We're going to take the unit, grams, N2, and we're going to pull it down to the bottom. Now the first thing to recognize here is that we are given information about nitrogen, but we're asked about ammonia. Anytime you go from one substance to another substance, you have to use the mole ratio, which means we have to have our nitrogen in moles. So that's our first step to stoichiometry, is convert our given to moles. So we put moles on top. Now remember, with grams, we use the molar mass off the periodic table. There's 2 nitrogens, so we're going to have to double the mass. Mole is 1 though, because 28.02 is the mass of 1 mole. Now when we multiply and divide, the grams would cancel, leaving us at moles of nitrogen, but we want information about ammonia. So now we're going to do step 2, where we have our mole ratio. We're going to bring moles of nitrogen to the bottom because we want to get rid of nitrogen, and we want to talk about ammonia. So we're going to put moles of ammonia on top. Now, when you have that mole ratio, that's when you use your coefficients from the balanced equation. So the number in front of nitrogen is 1, so we put 1, and the number in front of ammonia is 2, so we put 2. Again, we're doing this so that we can go from nitrogen to ammonia, and the only way to switch a substance is to use the mole ratio. So our given has to be in moles first. Now when we multiply and divide, moles of nitrogen will cancel and we're at moles of ammonia. Since the question asks for how many liters or volume of ammonia, we have one last step to do. We need to go from moles to liters. So we're going to toss our moles of ammonia down to the bottom to get rid of it. And since we want liters of ammonia, we're going to put that on top. Then we can look on page 1 of our reference table, and we see that 1 goes with moles and 22.4 goes with liters. So when we multiply and divide, the moles of ammonia will cancel, and then we can get our answer. So again, you multiply on the top, you divide the bottom, and we should have 22.4 liters. We used 3 significant figures because our mass had 3 significant figures. Our given had 3 significant figures. Now, it's just a coincidence that they're both 22.4. Just because this is an answer of 22.4 does not mean that's the answer every time. It just happens to be the same answer. Make sure that you have a list of questions written down next to your notes, or go back over the notes and write down some questions, and then come see me on Microsoft Teams or through Remind or through email, and let me know what questions you have so that I can try and help you understand how to convert pressure, temperature, and volume.